we have seen that when a shock wave moves through a fluid, it sets the fluid behind it into a motion. In other way, that when a disturbance moves through the fluid, it sets the fluid into a motion. Now, we would like to see that what would be the general form of this disturbance and what would be the subsequent motion in a general sense, because when a body moves through a fluid, that also creates a disturbance in the fluid in which we are interested, and the disturbances created by a moving body are also propagated to other parts of the fluid and also to the other parts of the body. And in general, the disturbance related to the fluid is a wave motion, and the speed of propagation of this disturbance is called the wave speed. Through this mechanism of wave propagation, various parts of the body interact with the fluid and also with each other, and the forces on the body are developed. Of course, the general problem is unsteady, and to study this problem we need to use the appropriate equations and solve them. Now, considering an adiabatic non-viscous motion in a constant area duct, we have the continuity equation d rho dt plus rho du dx plus u d rho dx equal to 0, and the Euler's equations or momentum equations as du dt plus u du dx plus 1 by rho dp dx equal to 0. Since we are considering an adiabatic non-viscous motion, the flow is isentropic, and consequently, the energy equation can simply be written as either H 0, that is the total enthalpy equal to constant, or entropy equal to constant. Since we are considering a non-viscous motion and adiabatic motion, the flow is isentropic and the isentropic conditions exist, and as you know that in an isentropic flow, in isentropic condition, pressure is just a function of density alone, and for a perfect gas this becomes P is proportional to rho to the power gamma or which we can write as P by P 1 equal to rho by rho 1 to the power gamma. This implies dp dx to be dp d rho and d rho dx, and since it is an isentropic process, dp d rho where dp d rho at constant entropy is the square of speed of sound, and this of course, we can substitute in the Euler or momentum equation and eliminate P with the help of this relation. Now, the disturbances or perturbations are defined relative to the fluid, that is at rest or at uniform motion. Let us take that initially the fluid was at rest. Consider the fluid rest initially, and the velocity is 0, and let us say density to be rho 1. Now, assume that the perturbed values are given by perturbed values are u and rho. Now, let us define rho to be rho 1 into 1 plus S bar. This S bar, the dimensionless quantity S bar as defined here is simply rho minus rho 1 by rho 1, that is normalized density rise, Note the use of this symbol S bar. Remember that it is not entropy, which is the normalized density rise or condensation, called condensation. When the value of this parameter is negative, of course, it represents a rarefaction. Substituting these into the equations, the continuity equation becomes rho 1 by dt plus rho 1 into and du dt for a perfect gas. We have P by P 1 equal to rho by rho 1 to the power gamma, which becomes 1 plus S bar to the power gamma, and T by T 1 is 1 plus S bar gamma minus 1. All these equations and relations are exact for frictionless non-conducting motion. However, the equations are not easily integrable as they are nonlinear. So, to solve these equations analytically we need to linearize them, and these equations can be linearized by a small disturbance assumptions. That is, we now assume that the disturbances are small, that is, we will assume in S bar du dx is much smaller than du dx, that is negligible when compared to du dx. Similarly, the term u ds by dx and u du dx are product of small quantities, hence they are negligible. Now, the local speed of sound a square, which is dp d rho, it can be expanded in a Taylor series about the mean state, that is undisturbed state in this case, which is dp d rho at 1 plus rho minus rho 1 a Taylor series expansion about the undisturbed state, and which is this gives that a square by 1 plus s bar into this, that is the last term in the Euler's equation can be approximated as a 1 square d s bar x. So, with these assumptions, the equations can now be linearized. So, the equations now linearized to the first term d s dt and the momentum equation become these equations are known as acoustic equations, because of very small disturbances or sound waves, that is the sound waves produces a very small disturbance, a situation like this, and hence the equations are called acoustic equations. Also that perfect gas equations can also be approximated as P by P 1 equal to 1 plus gamma S bar and T by T 1 is 1 plus gamma minus 1. Now, to solve this equation, we differentiate the continuity and momentum equations with respect to t and x. Differentiating the continuity equation with respect to t, we have and since the order of derivative in these two terms are immaterial, these results into similarly, if we differentiate the continuity equation with respect to x and the Euler's equation with respect to t, we will get an equation in terms of the perturbation velocity, which is again these are the well known wave equations. So, we see that the density disturbance as well as the velocity disturbance both satisfy the wave equation, and the disturbance propagate with a definite wave speed, which in this case is a 1 or the speed of sound. Now, the general solution for these wave equations are given as x minus u 1 t plus g of x plus u 1 t and u equal to f of x minus u 1 t plus g of x plus u 1 t, where f equal to u 1 f and g equal to minus u 1 g. Let us now analyze the character of these solutions, and for this purpose let us take g equal to 0. Let us take g equal to 0. So, the density disturbance at time t is given as simply f of x minus u 1 t. This represents a disturbance or wave which at time t equal to 0 had the shape, that is at t equal to 0 the disturbance had the shape and what we see that at time t the disturbance is exactly the same speed, but with the corresponding points displaced a distance a 1 t to the right. That is the velocity of each point in the wave, and hence the wave is a 1, which you can see that let us say that this is the shape of the disturbance at time t equal to 0 and what you see that the disturbance retain its same shape, but at all time the disturbances retains its original undisturbed shape, and the points displace a distance by a 1 t to the right, and hence we can say that the each point on the disturbance has a velocity speed of a 1, and hence the wave speed is a 1. A wave in which the propagation velocity is in one direction is called a simple wave. That is, if the wave propagates only in one direction, it is called a simple wave. So, in this case this is the wave which is propagating to the right is called a right running wave. Similarly, the wave described by so this is right running simple wave. Similarly, the other part of the solution g of x plus a 1 t represents left running simple wave. That is, in this case the wave is propagating to the left with speed a 1. The lines in the x t plane which traces the progress of the wave, there is the lines with slope dx dt equal to plus or minus a 1 are called the characteristics of the wave equations. That is, lines with slope dx dt equal to plus minus a 1 are characteristics of the wave equation. The disturbance propagates through the fluid with a speed, propagation speed or wave speed is square root of d p d rho, and this is called the acoustic speed or sound speed. The result is applicable to disturbances in which the velocity and temperature gradients are very small and u by a 1 is much smaller than 1. So, these are, as you have assumed for the purpose of linearization, that the disturbance speed or the velocity u is quite small, which now comes to be that u by a 1 is much smaller than 1, and in which the gradients of the disturbances, that is velocity, temperature, pressure, are all very small, and consequently the dissipative forces will have no considerable effect. In that situation, the results are applicable, that is, these acoustic waves solutions or acoustic waves are applicable where the disturbance is small and the gradients are also very small. So, that dissipative forces have no considerable effect, that is, the motion is isentropic, and as you have already discussed that the sound wave is isentropic. So, the result applies to propagation of sound wave as well, with the sound speed as given by a square equal to d p d rho at constant entropy. The amplitude of the ordinary audible sound is quite small and the local production of entropy is negligible. Friction and local entropy production is negligible for computing the speed of ordinary sound, but the cumulative effect on the amplitude is not negligible. The quantity square of the speed of sound provides a pressure density relation and eliminates pressure from the momentum equation, which we have already seen that d p dx was replaced by a square into d rho dx. Of course, when non-isentropic processes are present, pressure also depends on entropy and the relation is not correct. It has to be augmented by change in entropy change term. Now, A square can be evaluated from the equation of state, that is, for a perfect gas we know A square become gamma p by rho or gamma r t. Now, let us consider what happens to the velocity of the particles that makes the wave, that make up the wave, and also how does pressure changes. Now, the pressure and the pressure disturbance accompanying, so pressure change in a sound wave due to sound wave we have seen that P by P 1 is for small disturbance 1 plus gamma s bar, or this implies the pressure change is that is, the pressure wave has the same shape as the density wave. However, its amplitude is differ by a constant factor gamma. Now, as the wave progresses through the fluid, the pressure disturbance sets the fluid into a motion, and the fluid particle also undergoes a motion with its velocity being u, which is called the particle velocity u, and in general is much smaller. Fluid particle velocity u and it is usually much smaller than the speed of sound during the propagation of a sound wave. For a simple wave, the velocity disturbance is, as you have already seen, u equal to a 1 f x minus u 1 t for a right running simple wave. Which of course is equal to u 1 s. Similarly, for a left running simple wave, u equal to u 1 The various parts of the wave are called condensation and rarefaction, depending on whether this condensation parameter S bar is positive or negative, that is, whether the density is higher or lower than the undisturbed density rho 1. In combining the two, we can write that u equal to either plus minus u 1 s bar. The effect that the wave produces on the fluid, of course, depends on the gradient of this density and pressure distribution and on the direction of motion of the wave. Thus, the portion of the wave where density is increasing as it passes is called a compression, and that which decreases the density is called an expansion. So, the corresponding disturbance of particle velocity are given by u equal to plus minus u 1 s for the left and right propagating waves respectively. It may be seen that a compression accelerates the fluid in the direction of wave motion, whereas an expansion decelerates it. The non-simple wave is a superposition of two simple waves, that is f and g, and the relation between particle velocity and density is, for general non-simple wave, for general non-simple acoustic wave, u by u1 plus g. When the disturbances are vanishingly small, we can express these perturbation quantities in terms of differential, where u, that is the particle velocity u, and the condensation parameter s bar can be replaced by du and d rho by rho 1 for vanishingly small disturbance. And we have du equal to plus minus a 1 s, which can be written as plus minus a 1 d rho by rho 1. Similarly, the pressure changes is d p by p 1 can be written as gamma d rho by rho 1, and combining the two, these together also implies that d p equal to gamma p 1 by rho 1 d rho that is a square d rho and it becomes plus minus rho 1 a 1 d u. And these relations holds for infinitesimally small disturbances or very small disturbances. Now, this solution of wave motion can be used to study some of the very important problems, and one such problem that we will be handling here is the shock tube problem. Now, shock tube is a very simple device. Shock tube, it is a simple device consisting of a tube that is divided into two parts by a membrane or a diaphragm, in which pressures are different. That is a simple device consisting of a chamber of a consisting of a tube divided into two chambers by a diaphragm. And the pressure is different in the two chambers. That is, we can have a shock tube is simply this, a diaphragm here, and the pressure here are different, say P A, P B. Usually one side is a very high pressure and the other side is low pressure. Now, since we have discussed about linearized wave motion, we will consider this as a linearized shock tube. We will consider a linearized shock tube, that is, in which linearized shock tube, that is, that P B minus P A is very small. That is, let us say that the initial pressure distribution in the tube, is that is, at t equal to 0, there is a step distribution of pressure, where the low pressure side has the pressure P A and the high pressure side has the pressure P B, and at t equal to 0, the fluid particles are not in a motion, that is, the particle velocity is 0 everywhere. Now, let us say at that instant we suddenly remove the diaphragm or the membrane, and consequently now a fluid motion will set in which fluid from high pressure region will try to flow through the low pressure region. Now, as you have considered the disturbance very small, so this disturbance, that is, the difference in pressure is very small. So, this disturbance, that is disturbance created by the removal of the diaphragm, also satisfies the linearized equations and hence the linearized solution. Let us say at time t equal to 0, the solution is described by solution, that is a wave at t equal to 0 is S bar at x 0 equal to f x plus g x, we call this to be S 0, and obviously the density will also have a step distribution corresponding to the pressure, and let us say this is S b for x greater than 0 and it is 0 for x less than 0. The particle velocity is 0 everywhere. So, can write a 1 f x minus a 1 d x equal to 0 for all x. Solving these two simultaneously, what we get is that we get f x equal to g x, and this is half S 0, which is half of S b for x greater than 0 and 0 for x less than 0. The motion at any subsequent time t will be given by S bar x t equal to half x minus a 1 t plus half and substituting to these values, this will be S b for x greater than a 1 t for x greater than a 1 t is half of S b bar for minus a 1 t less than x less than a 1 t and 0 for x less than minus a 1 t. Similarly, the velocity will be half of a 1 is 0 x minus a 1 t plus half of s 0 half a 1 is 0 x of s 0 of x plus a 1 t, and this will also become 0 when x is greater than a 1 t minus half a 1 s b bar for minus u1t less than x less than u1t, and again 0 for x less than minus u1t. That is, we can see that at any time the density or and this is the solution at time t, that is density distribution and the pressure distribution and velocity distribution are also similar. That is what we see, that starting from the initial time and expansion is moving to the right in this case, and a compression is moving to the left. So, that a density on the left part is gradually increasing, and on the right it is decreasing, or we can say you can have, let us say at this is t equal to 0, at t equal to t 1, that is a compression wave is propagating to the low pressure side, and an expansion wave of equal strength is propagating to the high pressure side. Now, what we have covered today is basically a wave motion in one dimension, where we have first linearized the continuity equation and Euler's equation, assuming that the disturbances are small, and we have seen that the disturbance propagates with a constant wave speed, which happens to be the speed of sound, implying that the small disturbance waves are isentropic and acoustic wave. We have also seen that for the linearized wave equation or for the linearized wave problem, the wave retains its shape at all time. For a wave is called simple if it moves in only one direction. So, we can have in one dimension both left running and right running simple waves, and a general non simple wave is a combination of the two, where wave propagates in both the direction, that is to the left as well as to the right. We have then applied this linearized solution to a linearized form of the shock tube, where we have assumed that the pressure in the two chambers, that is in the high pressure chamber and low pressure chamber, are marginally different. So, that when the diaphragm is removed, small disturbance or linearized wave propagation sets in, and consequently, we have what we see that we have a compression wave propagating to the low pressure side and an expansion wave propagating to the high pressure side, and how the step distribution of pressure and density is going to be eventually smoothed out.